have a rectangular grid of squares, 141 rows, 91 columns. Each square has room for 2 numbers. Horace and Vera each fill in the grid by putting the numbers from 1 through 141 times 91 into the squares. Horace fills the grid horizontally, puts 1 through 91 left to right in row 1, 92 through 182 in row 2, so on. Vera fills the grid vertically, puts 1 through 141 top to bottom in column 1, then 142 through 282 in column 2, so on. How many squares get 2 copies of the same number? So we can just try a smaller example of what's going on. So first off, we can ignore the fact that like Horace and Vera are writing in the same grid. It's a little bit confusing. We can just imagine 2 separate grids. So like here's a good example. We could do 5 by 3s. This would be fine. Okay. So just as a smaller example, it's often helpful to do a smaller example to try and understand the problem. So what is Horace going to do? Well, Horace fills the grid in horizontally. So he writes in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And Vera writes them in vertically. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And now we can ask ourselves how many squares receive the same number in both grids. Well, we can see that the 1s are in common, the 8s are in common, and the 15s are in common. So in this case, the answer would be 3, right? So if we replace the 2 numbers, 141 and 91, with 3 and 5, then we would just get the answer 3. But unfortunately, we're working with much larger numbers, so we can't write in the numbers manually. So how do we handle this? Well, we want to come up with a sort of formula that gives us for any square like r comma c, where r is like the row number, c is the column number. If we can have a formula in terms of r and c that tells us what the value in r comma c is, that would be very useful. So let's think about it in this problem, and then we can replace the constants of 3 and 5 that we get in the formula with the original 141 and 91, and that will actually lead to us solving the problem. So this is what I mean by that. So we can write in the column numbers here, row numbers 1, 2, 3, 4, 5, column numbers 1, 2, 3, and in general we can just let the coordinate be r comma c. Okay, 1, 2, 3, 1, 2, 3, 4, 5. And we're going to see that there is actually a linear relationship here, right? Like in terms of R and C, that gives us the entry of the grid, right? So let's first work with Horace's grid. So Horace works filling in the numbers horizontally, right? So in the spot, so 1 comma 1, he puts a 1. In the spot 1 comma 2, he puts a 2. In the spot 1 comma 3, he puts a 3. So hopefully you can see the pattern here. Basically, in the first row, in the square that is like r comma c, he always puts in the number c. Okay, let's move on to the second row, where we see now 2 comma 1 gives us 4, 2 comma 2 gives us 5, and 2 comma 3 gives us 6. So now we can see that r has shifted up by 1, and as a result, the numbers that he's putting into the squares has increased by 3. So what does this tell us? Well, this means that r should get a weight of 3. Yeah, so basically every time r increases, it should be 3, right? So like let's say this is like the entry formula, entry in the grid for r comma c, right? So there should be like a 3r in the formula because every time r increases by 1, the entry he puts in increases by 3. And there should be a plus c here because every time c increases by 1, the entry increases by 1. Okay, and now we just have to adjust this by a constant, right? So in this case, for example, if we try 1 comma 1, we get 4 instead of 1, right? So we have to subtract off 3 here. And now if we just try values, like through this, I mean, I didn't really rigorously show why this formula works, but hopefully it's convincing enough that every time we increase r by 1, the entry he puts in increases by 3. Every time we increase C by 1, the entry he puts in increases by 1. So as a result, it should be like 3R plus C plus or minus some sort of constant, and then we solved for that constant. And now if we just try different values here, we will always get the right answer. So if we try like ask ourselves, what's 2 comma 2 here? Well, it's just going to be 6 plus 2 minus 3, which is 5. So that works just fine. And in general, for all the entries of the grid, it's going to work. Okay, so I'm going to actually, instead of E, I'm going to let this be a function, right? So this is really what we created is a function for what Horace writes in the R comma C value, right? So we can write, this is like a function, like H of R comma C. Okay, well now we want to find our V of R comma C formula. So I'm not going to go through all of these steps again for just to make things more simple and not write too much on the board. But basically the process is exactly the same, right? So every time the row number, right? So these are the row numbers. Every time the row number increases by 1, the number Vera puts in increases by 1. So there is an R. And then every time the column number increases by 1, the entry increases by 5. So there should be a 5C. And then we try the constants or whatever, and we see that, well, in the 1 comma 1 spot, currently this formula gives us 6. So we need to subtract 5. We need to adjust by 5 in order to give us the right value. So now, in total, what can we do once we have these two formulas here for the entries, like in terms of R comma C? Well, we can just set them equal to each other, right? So we get H of R comma C is equal to V of R comma C. And that's going to give us 2R is equal to 4C. Well, actually, let me just write out the full formula and show how the simplification works. Okay. Yeah, so basically, 3R plus C minus 3 is equal to R plus 5C minus 5. So if we subtract everything, we get that 2R plus 2 is equal to 4C. All right, yeah, so we can factor out, we can divide out by 2 on each side, and we just get R plus 1 is equal to 2C. And so now we can just try all the values of R and C, right? So we know that R should be any value from 1 to 5. C should be any value from 1 to 3. And so now this is just like a linear sort of relationship, right? So for every value of C we plug in, we get a value of R, right? So we can try C equals 1, that gives us an R value of 1, right? Corresponding to the 1 comma 1 entry. If we try C equals 2, that gives us R equals 3. That gives us the 3 comma 2 entry. And if we try C equals 3, that gives us R equals 5. And that gives us the corner entry, the 15. So now that we have done like this sort of like method here, right, for 5 and 3, now hopefully you can see how to solve it also for the 141 and 91 case. So let's try that now. We're only going to need some minor adjustments to the formulas. Basically, let me just erase everything in the box because there are no longer just 15 numbers in the box. So we can't really think about, but you can imagine those numbers in the grid still being there. Oops. Um, yeah, so now I'm going to replace these with dot 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 numbers. So instead of going from 1 to 5, there are 141 rows. Okay? And instead of 3 columns, there are 91 columns. Okay, very large, scary numbers, but the method is still exactly the same here. So remember, Horace writes the numbers 1 through 91, and then he writes 92, etc. Vera writes the numbers 1 down to 141 and then writes 142 over here. Okay, so now we have to modify our H and V formulas, right? So instead of 3 and 5, you're going to notice they're going to look very similar, except the constants are just replaced with 91 and 141. So H of R comma C, what's happening here? Every time, so remember these are the R values, these are the C values. Every time we increase R by 1, the value of in the grid goes up by 91. So we have 91R. And then every time we increase the C value, the entry in that square goes up by 1. So it's 91R plus C. And then we just have to subtract 91 in order to make the 1 entry a 1. And similarly here, we get R plus 141, C minus 141, right? Because every time we increase the column number by 1, we go up by 141. Every time we increase the row number by 1, we go up by only 1. And the 1 entry should be a total of exactly 1 in the corner there. Okay, and then we just set these equal to each other. And when we eliminate both sides, we get 91r plus 50 is equal to 140c. We can divide out a factor of 10 here. And now, once again, we just get this sort of linear equation here where we can just like increase the sort of values. So remember the first solution of r comma c is just going to be 1 comma 1 because they both write a 1 in the top left corner. So 1, 1 is the solution. Okay, the next solution, keep in mind since this is 9r and this is 14c, then any sort of solution, we can raise this number by 14 and raise c by 9, and in total it'll raise both sides of the equation by 14 times 9. And there's actually a very simple modular argument you can make why you have to raise r by like 14 at a time and c by 9 at a time, right? So like the idea is just if you take everything mod 9 here, for example, you get 5 is equivalent to 5c mod 9. And that tells you that c is equivalent to 1 mod 9. So you can only try c equals 1, 1, 10, 19, etc. Okay, so we raise c by 9, and then as a result, r gets raised by 14. We raise c by 9 again, r gets raised by 14. And the question is, when does this process end? Well, it ends when we get to the other corner of the grid, at which point we will get the solution 141, comma 91. And the question is, how many solutions are there in this range from 1, 1 up to 141, comma 91? Well, we can just ignore the left entries and instead just think about these like arithmetic progression of numbers like adding 9 each time. So in total, we added 90 and we add 9 at each step. So we had 10 total steps. So 10 steps between the pairs means that there are a total of 11 pairs. And that's just our answer, 11. Okay. Now, number 24. So we have a frog hopping along the number line, and it starts at 0. If it's at 0, moves to 1 with probability 1/2, and disappears with probability 1/2. And then for each of n, 1, 2, 3, if it's at n, then it moves to n plus 1 with probability 1/4, to the previous number with probability 1/4, and disappears with probability 1/2 once again. So what is the probability that the frog reaches 4? So this sort of problem I've seen time and time again on the AMC, and it's a little bit complicated because if you just try to solve the problem in the simplest way possible, you're gonna run into issues. So what I mean by that is like let's just change the problem statement slightly, right? So instead of it being like this, where we move to n plus 1 probability, let's just say that instead we had it moves to n plus 1 with probability 1/2, and it disappears with probability 1/2. Well, in this case, it would be very easy to solve the problem, right? Because we just start at 0, and then we're like, what is our probability that the frog makes it to 1, right? Or instead of vanishing and not making it to 4, well, there's a 1/2 chance. And then the probability of making it to 2, well, that's a 1/2 chance. Probability of making it to 3, that's another 1/2 chance. Probability of making it to 4, that's another 1/2 chance. And so the answer would just be 1 in 16. Um, but the issue here is that so the reason why this is so simple is that we can't go backwards, right? There is no possibility of going back to n minus 1. And that makes the game very easy because once you're at a game state where the frog is at 2, for example, you're never going to go back to a previous game state where it was 0 or 1, right? There's a very linear order to things. You can't go back to previous parts, and so the probability works out very nicely. So the issue with the actual way the problem is stated is that if you just try to solve the problem this way, you're not going to be able to. So if you start at 0, you're like, okay, what is the probability that the frog makes it to 1? Okay, 1/2. What is the probability that the frog makes it to 2? 1/4, right? But the issue is that 1/2 times 1/4 is 1/8 is not the entire probability that the frog reaches 2, right? Because there's also the 1/4 chance that the frog goes back and then a 1/2, 1/4 chance that it makes it all the way to 2, right? So we have to add that in. So it kind of becomes this infinite amount of like numbers that we have to sum, right? So there's a 1 in 8 chance that the frog goes from 0 to 1 to 2. There's a like something like a 1 in 64 chance that the frog goes from 0 to 1 to 0 to 1 to 2. And you're just summing up an infinite amount of numbers. And there are infinite series that can handle just this case where you only have three numbers, right? You can write it as a geometric infinite series and sum it. But the problem is once you add a 3, this problem becomes exponentially more annoying. Because you could have paths where the frog goes like 0 1 2 1 0 1 0 1 2 1 2 3, right? And there's just too many possibilities to count, literally. You're not going to be able to sum this huge infinite number of terms you get within the finite contest time. So we need a different strategy here. In particular, what we can think about is the idea of a system of equations, right? So in particular, what I mean by that is if you have something like 3x is equal to 2 times x plus 5, right? Your response to this sort of problem isn't just like, okay, we have a variable x, and we just need to solve for x. But wait a minute, x appears on the other side of the equation too, right? How are we ever going to solve this? Well, no, you can still solve this, right? You just move all of the x terms to the left side and solve the system of equations, right? X equals 10. So in a similar way here, if we let variables represent the probabilities, then we can just plug in those variables of the previous game states into its own equation, right? So let me explain what I mean by that. Well, let's say P, so let's look again at the like simpler version of the problem where we're just looking for the probability that the frog reaches 2, right? So we can let P be the probability that we're looking for, right? That the probability that the frog starts at 0 and makes it to 2, and Q is the variable that represents if the frog if the frog starts at 1 and makes it to 2. So we can be like, okay, the probability that we make it to 2 from P is just, well, we have a 1/2 chance of not disappearing, and then we make it to Q. And from there, there's a Q probability that it works. And then we're like, okay, what is Q? Well, Q is the probability that we make it to 2, right, from Q. So there's a 1 in 4 chance that we go back to 0, and then there's a P chance that we make it to 2. And there's a 1/4 chance that we go to 2 right away. And then in that case, the probability is 1 or 100%, right? Because the probability that you reach 2, given that you are currently at 2, is 100%. You're already there. So now we get, a system of equations in two variables, and suddenly what was this huge infinite number of sequence of terms is actually handled very conveniently in just two equations. So it's this sort of method that instead of making the number of like possibilities that can happen like blow up infinitely and it's basically impossible to sum, we just have a number of variables equal to the number of game states. So we can create a slightly more complicated version of this by having 0, 1, 2, 3, 4, right? We can let the variables now be like P0, P1, P2, P3. Once again, the probability that we reach 4, given that we're at 4, is just 100%. We can keep that in mind. So now we can write out the equations, right? So P0 is equal to, well, there's a 50% chance that we go to 1, and then in that case, there's a P1 chance that we make it to 4. Well, P1 is just there's a 1/4 chance we go to P0, and there's a 1/4 chance we make it to P2. Or we make it to 2, sorry. These represent the probabilities, but we're going towards the numbers, right? So there's if we are at 1, right? What is the probability that we make it to 4 given that we're at 1? Well, there's a 1/4 chance we go to 0, and then there's a P0 chance, and there's a 1/4 chance that we go to 2, in which case there's a P2 chance. And you'll notice I haven't been writing this down, but there's secretly this extra third term, right? That's like there's a 1/2 chance that we disappear. But in that case, the probability that you make it to 4 is 0, because if you're gone, then you're not playing the game anymore. You're gone, right? So this just cancels out. It goes away. So we're just ignoring that term in all the equations. Okay. What is P2? Well, very similarly to the previous equation, it's going to be 1/4 P1 plus 1/4 P3. And finally, P3 is going to be equal to 1/4 P2 plus, and then 1/4. Like 1/4 times 1 right? Because 100% chance once you get to 4, we can just get rid of that. All right. So now we just need to solve the system of equations. And you'll notice there are four variables, P0, P1, P2, and P3, and four equations. So in theory, hopefully, assuming that there's no like contradiction or some like tautology in the system of equations, right? Like in secret, maybe it says that like a plus b is equal to 2, c is equal to 3, a plus b plus c is equal to 5, or something like that. And then in that case, you wouldn't be able to solve the system of equations because this equation doesn't give you any additional information. But as it turns out, this is not the case here. All of the like linear equations give you different information about the variables, and you can solve it to find what all four variables are. But keep in mind, what we're trying to solve for here is P0. So, like the strategy that I would do here in order to solve it as fast as I can is to eliminate the variables from P3 towards P0. So our first goal is to eliminate the P3 variable. So if we multiply this equation by 4, we get 4P2 is equal to P1 plus P3. And now here, by plugging in the value of P3 into the equation, we can like combine these two equations. So we get that 4P2 is equal to P1 plus and P3, but instead of P3, we write in 1/4 P2 plus 1/4. And we can just cancel that out and, well, not cancel that out, but I mean like combine like terms. And that will give us 15/4 P2 is equal to P1 plus 1/4. Right. Okay. So in this case, we've basically eliminated all of these equations, and now we have three equations to work with. Right. So now we want to eliminate the next variable in the list, right? P3, P2, P1, P0. So next up on the cutting board is eliminating P2. So what we can do here is we can multiply everything here by a factor of 15. And now here we would get 15/4 P2, but instead of writing 15/4 P2, I'm going to write what this equation says it's equal to. So P1 plus 1/4. Okay, the P1 cancels out and goes to this side and makes this a 14. So now we get 14P1 is equal to 15/4 P0 plus 1/4. And finally, we just have two equations left, right? So this goes away, this goes away. And our final step is just to combine these two equations. We want to cancel out the P1s. So we can multiply this by 28. And we know that 14P1 is actually just equal to 15/4 P0 plus 1/4. So now we can just solve the system of equations. Well, it's a system of equations of one equation in one variable, right? So as I mentioned all the way at the start when we were talking about like an equation involving x, right? I didn't just bring that up for no reason. It's because eventually you just get an equation in one variable by canceling out all the other variables, and then you can just combine the like terms and find the answer, right? So 28P0 is equal to 15/4 P0 plus 1/4. I'm going to multiply everything by 4 just to make things a little simpler. So I get 112P0 is equal to 15P0 plus 1. And we get 97P0 is equal to 1. So therefore, P0 is equal to 1 in 97. And that's our answer. In general, this method of creating probabilities and like finding formulas that connect them with each other, this is called Markov chain. All right. So if the AMC went well for you and you qualified for the AIME, make sure to check out our latest AIME preparation book with 5 practice tests to help learn more of these sort of difficult techniques to solve hard AIME problems. And you can look on MathTopia Press on Amazon to see our full previous collection of AMC preparation books full of practice tests and detailed solutions.